Good day, everyone. This project focuses on energy rescheduling in cloud data centers using first fit decreasing, best fit decreasing, and genetic algorithm approaches. The goal is to reduce energy consumption while maintaining efficient server utilization and minimizing SLA violations. First, we initialize the environment by importing the required libraries such as matplotlib, numpy, random, and preprint. We also set random seeds to ensure reproducible results. After that, we define the datasets, server capacities, and the energy model parameters, where servers consume 100 watts when idle and 300 watts at full capacity with the SLA threshold set to 90%. Next, we implement the energy modeling and genetic algorithm fitness functions, including server allocation, power computation, SLA violation detection, and fitness evaluation. We then implement the helper functions for first fit decreasing and best fit decreasing. FFD places tasks in the first available server, while BFD places them in the tightest fitting server. Both algorithms sort tasks in descending order before allocation and have a time complexity of O of n squared with the space complexity of O of n.
To tackle the energy optimization problem, we implemented a genetic algorithm. The process starts with a population of random solutions that evolve over several generations. We use a crossover operator to combine pair solutions without duplicating tasks, and a mutation operator that randomly swaps tasks to ensure we don't get stuck in local optima. The genetic algorithm energy function manages this entire solution using a descent to make sure our best performance results are never lost. In terms of performance, the algorithm has a time complexity of O of g times p times n squared, and a space complexity of O of p times n. To see if this complexity actually pays off, we compared our GA against two industry standards, first fit decreasing and best fit decreasing. We use a calculate metric function to track the big four: active servers, resource utilization, total power consumption, and SLA violation. Finally, we ran these algorithms across multiple datasets using run experiments. To make the dataset digestible, we built a plot dataset analysis function. This generates the visualization you see here, specifically focusing on power consumption and GA convergence. This graph clearly demonstrates how the genetic algorithm refines its strategy over time to find the most energy-efficient scheduling path.
We will now run the entire notebook, so let's start. For the small dataset with 50 tasks, the FFD and BFD both use 9 servers and consume 2,576 watts, but this resulted in 8 SLA violations. The genetic algorithm performed better by using only 5 servers, reducing power consumption to 1,312 watts, and lowering SLA violations to 3. It required slightly more execution time. Next, for the medium dataset with 200 tasks, the FFD and BFD show moderate improvements, while the genetic algorithm against achieved the best optimization with fewer servers, lower energy consumption, and fewer SLA violations. For the large dataset with 500 tasks, the FFD and BFD both use 88 servers and consume over 26,000 watts. The genetic algorithm used only 6 servers and reduced energy consumptions by around 94%, while maintaining low SLA violations. These charts summarize these results by comparing server usage, power consumption, execution time, and the convergence performance of the genetic algorithm.
The output of our program matched the theoretical expectations discussed in our report. Both FFD and BFD have a time complexity of O of n squared, while the genetic algorithm has a higher complexity of O of g times p times n squared, because it processes multiple generations and populations. In the results, FFD and BFD executed faster, while the genetic algorithm took more time, especially on larger datasets, which confirmed of TRN analysis. For the time complexity, or S of n, FFD and BFD only store task allocations, giving them O of n, while the genetic algorithm stores multiple populations, resulting in O of p times n. Although the genetic algorithm was slower, it achieved better energy optimization and server utilization. The GA convergence graph also showed decreasing fitness values over generations, proving that the algorithm improved its solutions over time. Overall, the outputs successfully validated the theoretical expectation from our report. That is all. Thank you.